Okay. Okay, I'll get started. So we were doing this, right? So we know, so I talked about the capacity of this collection. Um, this is definitely, we have shown the achievability of the latter quantity. So this is, I'll just write it, the delta can be made arbitrarily small, so I'm writing that. Um, so, so I did this in the one in the 10-15 minutes where the network was disrupted, but I'll just state this once again. So let's look at a more general problem. Look at a more general scenario. So E is a CPTP map. Okay, so CPTP map, and so Alice is here, and she can prepare any quantum state. So this is your E. So in N channel users and let's say CPTP users, she can input any state HA tensor N, and so Bob receives E of so if she prepares state, let's say omega, then Bob receives E tensor N of omega. Okay, so E is known to everyone. And so what is the goal? So Alice is receiving k bits. I mean, this keeps going on, but for n channel users, let's say she receives k bits, and Bob wants to reconstruct. So the protocol is so any so the protocol is as follows. So you have k bits. So for each of these k bits, so let's take any to be k. So you will prepare a row B living inside HA tensor N, and row B is input into this. So row B is, so let's say, I'm just going to denote this as a big particle. So this is characterization is row B. So this is input into this CPTP map. So out comes E of E tensor N of row B. And so you have to design a measurement now. So POV. Yeah.
Even that should be E tensor N, right? E going from L of HA tensor N to L of HB tensor N.
Yeah, okay. Thank you. So E tensor N is just EE operated on each copy. Okay, good. So I am looking at a POVM. So lambda B. So I'm looking at a POVM, and what do I want? I want the following, right? Desire that if I look at 1 by 2 power k overall bits, I'm looking at trace. This should be small. This should kind of fall with some positive quantity. This is the goal. This clear?
Yes, sir.
Okay, I'll just pause for 2 seconds and then carry. Okay. So what we can, so naive scheme, right? So naive scheme, I'm going to say, so pick some set, arbitrary set. Okay, I'll just, to give you an example, write this in gray. You can just take A1, A2 to A cardinality of X. Pick some arbitrary set. Okay, pick some operators. So let's say row A. So I'll say row X. Pick some arbitrary, doesn't matter. Pick some distribution. Okay. And so what you do is you just say, there exists. So the capacity theorem says, and okay, let's define sigma X as E of rho X. Okay, I should have named it rho X and sigma X. It's okay. So I define this. Okay. Now claim I'll make a simple claim to begin with. By this choice, I can communicate. Should I put all this in black actually? Well, it's okay. I can communicate at rate that is k by n arbitrarily close to S of Px of x sigma x minus Px of x S of sigma x. So I can get k by n arbitrarily close to this. Remember, I can generate 2 power k. Remember, I can generate 2 power n times so many states. Distinguishable states. Among these states, sigma, so among all these collections, among all this collection, I can pick out so many states that are distinguishable, right? And for each one of these states, I will map a B1 to Bk. So this thing can be written as 2 to the power n times k by n, right? Because my k by n is this quantity. So I can write 2 power k as 2 power n times k by n. And this is 2 power n times this quantity. right? So that means I can, so K by N close to, this is achievable. Where sigma x is defined as E of rho x. So you chose an x, you chose a px, and you chose a collection rho x, and you defined your sigma x to be E of rho x, and you can achieve this rate. So in n channel users, you can let n times this quantity, which I will call the C of P and the collection sigma x. Sigma, I'll just call it sigma script x. So I can achieve so much rate. How many of you are okay with this? If you agree, just put a thumbs up. Hey, Niranjan, you have any question? Okay, I'll move on because he's not responding. Okay, so now, well, I chose something, right? So I can choose the best. So K by N can definitely be greater than, greater than, so any K by N that is little smaller than soup over all choices of your set X, over all choices of your distribution on that set X, and over all choices of your collection rho X, right? So you choose your set first. You can do it in any order. I look at this. This is achievable, right? Because I can choose my best. Okay, so the question is this the capacity? So so I will call this alpha of achievable, right? It is, you can achieve at that rate. Alpha of E, because E is sitting there, and so I'll say it's alpha of E. So the question is the capacity of this map E equal to alpha of E? Okay, and so this was a kind of an open question for a long time, and Hastings, I think this is in 2008, he showed
Sorry,
that, yeah.
This C of E was defined to be that C of E was defined to be that thing on the right hand side.
No, I'm sorry. So I haven't defined C of E explicitly. So C of E is the maximum rate at which you can communicate over that CPTP map.
Oh,
Okay?
using this E. Okay.
Using this E. So if you want, I can, our definitions are going to be analogous to what we did in a few classes ago. Remember, we did definitions for a CQ channel. That is, you have a collection row X belonging to X, and you you define the capacity of this CQ channel, the capacity of this channel to communicate classical bits. And we defined this. And I said there are two, I think this is lecture 19, if I'm right. I think it is lecture. I think it is 12th March, maybe. No, this was the packing lemma. So we did before that. That is maybe 11th March. So think. Yeah, this was our capacity definition. So we defined the capacity of this channel. So similarly, so we say the maximum sup is the capacity. The rate R is achievable. The supremum of all achievable rates is the capacity. So similarly, we can define the capacity for this E channel, right? So essentially what you want to do, you want to find the maximum number of distinguishable preparations where the preparations are permitted to be anything inside this in N channel uses, right? That's your goal. So that's your capacity, that's your C. What I argued is that this value is achievable. So that means the capacity can only be greater than, because it's supremum of all achievable rates. I have shown that this is achievable. So the capacity is definitely greater than or equal to C of E. You agree with that, Tejas?
Yeah, correct.
Okay. So the question is, this is the conjecture, right? This is the question. Whether there is no other better scheme. The best scheme is to just do this. Nobody can do anything better than that. That's the question. Okay. Is it clear?
Yeah.
Okay. So it turns out it is not the capacity. So it turns out that this strategy that you tried is strictly suboptimal. So you can indeed do better on certain channels. So remember, this quantity, right? No matter what the E is, no matter what your CPTP map is, no matter what it is, you can compute this. I mean, in principle, there are a lot of supremums here, but this is a number that you can achieve. So what you should do, really, depending on that E, the sigma axis will look different and this value will look different. But I have got an expression no matter what the E is, right? You have to just go plug in that E. So you have to go plug in that E, compute this quantity, plug it in here, plug your PXs, and compute this quantity, and that number will be different. So for different E's, the numbers will be different. But this is kind of a universal formula, right? It's a universal formula. And what Hastings showed is, well, that is not a universal capacity formula, because there exists some channels for which I can do even larger than what you can do with that supremum. Now, why was this conjecture so hard to prove? Well, see, the problem is you have to show it is greater than this quantity, but this quantity itself is such a humongous beast, right? I mean, it is a supremum over a big collection of objects. So then, how do you get a handle on this, right? And then you want to show you can do better, right? Getting a handle on what is achievable itself is difficult. So how do you show something larger is achievable? So this was shown by Hastings, and I will tell you, I obviously will not do this, but I will tell you what you can wonder, okay, what is the idea? Right? Why is it that you can do better, right? Why is it that you can do better? It turns out, okay, so I should mention this, for the CPTP map, right? Suppose you're given this device that can only prepare these preparations. We showed this is achievable. We showed that this is achievable on that channel, right? So what is that? Say I'm going to write the same expression again: Px of A rho A minus Px of A S of rho A. So we showed that this is achievable. Now the question is, okay, on this channel at least, is this the best? And that turns out to be true. So the capacity of a channel specified through this collection is indeed the same. This is indeed, so I haven't shown the second direction where you have to show that if you take any rate greater than this, if I take any rate R greater than this, then somehow the probability of error cannot be squished down to 0. So recall, in my this lecture, right? I told you that the proof consists of two parts. I think it is the lecture 12. So like March 12. I think it is this lecture. So I told you that the proof consists of two. Not here. I think it was the. No, I think it was just 2 lectures after that. Give me 1 second. I think it is this. This is all the packing. 1 second. So we did this in 18th. Yeah. So if you see initially, just before this, I told you that there's something called an achievability. So the lecture 22. Where is lecture 22? Yeah. Okay. Here. So yeah. So the theorem, if you see exactly here, I have said that there are two parts to this theorem. So one is you show that if I take any r smaller than this quantity, which I have defined here, it is achievable. And if I take any quantity above than that, it is not achievable, right? And if you note, I only did one proof. I only did the proof of part one. I did not do the proof of part two. But I'm claiming here without proof, I'm just stating the result that this is indeed the capacity. So you cannot get greater than this. Okay, so on this channel you cannot. But why is it that on the E channel, Hastings could show that you can do better? Is not this scheme of trying to just choose an X, choose your best X, choose your best PX, choose your best thing somehow optimal? Why is it? Is this discussion so far clear? If it is, just put your hands up. If not, put a thumbs up. If not, tell me.
Sorry, I asked you one question. So in the HSW theorem, the row X's were being sent by Alice to Bob just as they are, and then Bob was distinguishing them, right?
Correct.
And in this setting where we have this E map, she's sending them using the CPTP map, not just as they are. And then Bob is distinguishing them. Okay, so that's the difference basically.
Correct. No, in the CQ channel setup, you don't have choices on the row axis. The specification gives you the row axis. You can only use this machine to put it in one of these X locations and design that state.
Okay, yeah. Those are fixed. The row X is fixed, and then you are just doing it. Okay, all the row X ends. Okay,
yeah,
they are fixed.
Yeah, so it's like, it's like the idea is like this. The machine can either prepare a use the note. So the machine can either prepare an electron with a spin whose axis is this way, or this way, or say this way, or this way. That's it. So this is your X corresponding to, say, X1, X2, X3, X4. She can only prepare these states, and somehow she has to distinguish them. Unfortunately, each one of them may not be distinguishable as is. So you make multiple big preparation and you send it. Is that okay?
Oh, correct. Yeah.
You can only prepare this. In the second state, you can prepare any spin axis direction. So, but only constraint here is that you have your density operator must live inside HA in one user and HA tensor N in N users. So kind of that's the way to think of it. So in the first situation, you could only prepare these. In the second preparation, you can prepare any spin and you can input it. But that is going to be perturbed because it's going to go through the E map.
Oh, yeah. So in the first thing, we had a soup only over the set X and the distributions on X, whereas here we have a soup on those two things and also the choice of row axis. We can choose the row axis as well.
In the first one, you had a soup only on your distribution.
Yeah. Oh, not even size
of. In the second one, you can choose your states also.
Yeah, correct.
but only thing is they have to live inside HA. Is that okay?
Yeah, then I think the alpha E would be bigger because you can also optimize over the row X choices.
No, I didn't.
Oh, sorry. I mean, so the question is that CE equal to alpha E? Oh, sorry.
So, see, this technique, what am I doing? I am taking some preparations, 1 letter preparations, and then I'm doing this, right? So I take a preparation for one instance, that is these collections. I choose my preparations for one instance. I choose my instances and my way of choosing those instances, right? And then I compute some number.
Yeah.
So the question is, why is this not good enough? Right? You understand now?
Yeah, I understand that, but this capacity of E is a bit unclear what that exactly means.
So in that, what I should do, I should generate my final goal in the capacity of E is to only identify row B belonging to 01K that are distinguishable when I come out of the E map, right? So these should be distinguishable.
Oh, okay. The maximum size of this set.
E tensor N should be distinguishable. What is the largest K for which I can find such preparations? So should be distinguishable, correct?
Oh, I see. Okay.
The A gives you one way of doing it. Pick some set X, pick some distribution, pick some preparations, and then you do it. But is that the best? And the answer is no. And I'll tell you why the answer is no. And that is, I mean, it turns out that this is a very important paper of Hastings. It's a lot of work that's gone on into Hastings' work.
Sir,
Yeah.
I had a question.
Yeah.
So instead of taking soup over sigma x, if we take soup over, instead of taking supremum over rho x there, if we take supremum over sigma x, will it make a difference?
Well, because it's there in the objective, you're essentially doing that, right? It's like,
but like after when we choose row x and afterwards if we pass it through a CPTP map, the distinguishability reduces. So
correct.
Instead of choosing row x first, if we choose what maximizes the sigma x first, will it make difference or is it covered in this?
It is covered, right? Because you choose a row x and then you will look at the objective function. You choose another row x. So if there is indeed, okay, so the idea is the following. So if there is indeed a row x tilde that are more distinguishable, right? So suppose there is a, so let's say there's a delta x tilde that are more distinguishable, okay?
Yeah.
The coming out of some row x tilde, right? It's coming out of some, let's say it's coming out of some alpha x tilde.
Yeah.
Okay. So you just put alpha x tilde here. So the soup will take it.
Okay.
So if there is some other collection that is more distinguishable, that is coming out of the CPT map, you just take those inputs here. So that soup would have come in here actually.
Okay.
Is that okay?
Yeah.
Okay. The key point is the following. So what is the, I mean, this is really the quantum part. See, the idea is when you do this, right? Okay, when you do this, what are you doing? You're going to all your technique is going to create one big x1 x1m. So x2m, it's going to create this x and m for each m, right? So you take one message, you will get this code word and you will prepare this sequence I equal to 1 through n row xi of m, right? That's what you will do. And you're trying to find that big collection of X and M's so that you are distinguishable. Correct? I mean, when it passes through the E map. That's what you're trying to do. But what you're not doing by this is you are not building an entanglement across the time steps. So maybe, so you're only accessing some space inside HA tensor N. That is, in some sense, only those that can be prepared by the product states. So if I take a completely entangled state living inside this, which cannot be written like this is a tensor product at the end of the day. So there is maybe an entangled state that is living inside HA tensor N, or a collection of entangled state that are more distinguishable than these preparations. So in other words, you have this huge HA tensor N. Through this process, you're only accessing some part of the possible preparations. Entangled states are not coming inside inside these supremum. And hence, what Hastings showed is that by inducing entanglement across, you can actually do better. Okay, so what you should do is not just the supremum over X, you should take a supremum over all preparations of your N state. So it cannot be written as a tensor product state, and that's essentially what he showed. So entanglement actually can increase capacity. Entanglement increases the achievable rate.
Sir, will it increase in the HSW theorem also?
No, it doesn't increase in the HSW. In the HSW, you are forced to send rho xn for some xn, right? You are forced to send this.
Okay.
You can correlate. That means, see, rho. So you can send. So you can choose your code words to be 000111000. You can choose your code word to have some pattern. So that means when you send row 0 tensor row 0 tensor row 0, you know the next one is going to be row 1 tensor row 1. So there is a relationship between the classical bits. So there is some kind of a relationship between the preparations, but they are not entangled. Entanglement is something more than just correlation.
Yeah.
That is what is going on. So see, row 0. So the preparations are correlated. So the multiple preparations are correlated, but the entire system is not an entangled system. This is exactly what he showed. So with by building this correlation, you can correct errors, but with entanglement, you can actually go further. Increases achievable rate over general CPTP maps. This is what Hastings showed. This was in 2008. And I mean, if you're interested, I can give you some more pointers. But did you get the general idea? I mean, obviously, I'm not going to go into the details, but did you get the general idea?
Yeah. Yes.
Okay, just one question.
Yeah.
So in HSW, you said we are forced to do this kind of product states, row 0, tensor row 0, and so on.
Yeah, correct.
So why can't we why can't we wait for all the n bits to come? We don't produce them as they are coming in real time, and after all of them come, we can make some entangled states and then send them.
No, hold on. You are doing that. Remember, you are waiting for B1 to BK, and then you will choose the code word corresponding to it. Remember, this is what you're doing, correct?
B1 to BK is the message, and then you create this.
Yeah. Remember, there is correlation between the bits. It can't be completely independent. Then you're simply using the channel every time, right? Remember, the most naive code. Your most naive code was this, correct? You take 2 bits. You want to reduce the error. What do? You repeat 5 times, correct?
Yeah.
This was your most naive code. Remember, you are building correlation between the bits. So if you send 0, you're sending 0 5 times, right? Similarly, if you look at this code book, right, the code book has, there is redundancy built into the code book. So that means redundancy means what? If I know the first symbol, I know something about the second guy. I mean, every guy, I mean, you're not going to take every possible combination. So there is indeed, you wait for the entire bit string and then only make your preparation. But still, you can only do this, right?
Okay. You
For
cannot.
some choices of x1 to xn, you are building in correlation in choosing your x1 to xn, but your state is still separable. See, that's the difference between quantum and classical.
Okay.
So it's
So in the
classical
second thing
correlation, but not quantum entanglement.
Okay.
So, for example, if you could prepare only these states, right, you could never prepare this state. So suppose your row 0 was this and your row 1, just imagine. If you, these are distinguishable luckily, but just imagine, you can never prepare this state and send it on the channel. Can you?
Yeah, you can't.
You cannot. You can only prepare this. You can prepare this. You can prepare this. And you can prepare this. You cannot prepare this. So similarly, what preparations you can do with this are kind of limited. If you are fixed, if your machine fixes what you can do, but if your machine does not fix and gives you preparations for n duration, right, then you can prepare entangled state. You can prepare something like this, and possibly there are states that are, you know, more separable. It turns out in this example it is not, but you understand?
Sorry, I think my connection went for the past 5 seconds or something. Can you just repeat for this?
Yeah.
I couldn't hear you.
So you understood this example, right?
Yeah, that 0 0 plus 1 1 by root 2 can't be sent. Correct.
Cannot be sent.
Yeah.
So all that you can do is you can do these preparations. You cannot do an entangled preparation. So you can build in correlation between your choices of the index, but you cannot build in quantum entanglement.
Yeah, correct.
That is
they're separable, correct.
Yeah, and possibly you can get quantum entangled, collection of quantum entangled states that are more separable.
Oh, so that's what the E does. The E channel sort of takes in some rows and makes them, output is entangled. The sigma x's are entangled.
Correct.
Okay.
And so this supremum is not going to do, because essentially your technique here in this alpha technique, the technique is you take one preparation and you kind of do some concatenation of those those one letter preparations. So it turns out this is not optimal. You try to entangle, because now you are not constrained by a machine, you're constrained by anything that you can prepare over HA tensor n. So which means you can prepare entangled states, and it turns out that entangled states can be separated better. I mean, by increasing your choice, you're actually doing better. Is that clear?
Yeah.
Yeah, obviously I'm not giving the proof, but if any of you take this up and prove it, it's like, I mean, if you can do the, if you can actually study through this, it's extremely good. I mean, so there is a, so there were a huge number of conjectures actually that were kind of related to this conjecture. So the conjecture really was, you know, is alpha of E equal to C of E, and this conjecture was not resolved for some time, and people showed there are a lot of conjectures that are equivalent to this conjecture, and it turns out Hastings showed that this gave an answer to this thing. And so there is one book by Hayashi, and in chapter 8 of that book he actually equates many conjectures. So he says, you know, if I can solve one conjecture, I can solve many conjectures, and then he shows that Hayashi proved it and things like that. So if, you know, just for people who are interested. So this is actually chapter 20. So what I have covered is essentially chapter 20. Okay, I will just pause for few seconds if there are any thoughts, questions. This is really a quantum nature of the problem because you really bring in entanglement, which you cannot do on a classical channel. Okay. So I think, okay, so let me just ask, is the question setting answer all that clear? I mean, the details obviously are not, but at least the broad picture. If it is, just put a thumbs up. Okay, great. Okay, I will go ahead. So next we'll do Schumacher compression. So remember, yeah, I'll do Schumacher compression, which is chapter 18. Very simple, much simpler than this. So the idea is the following. So what was our? So ours was a channel communication problem, right? So far. So you have bits coming in and you want to send it across. And you want to send it across, and you have some either a CQ channel or you have a CPTP map, and you're trying to understand how many bits I can communicate per use of this resource. This is a communication resource. Okay, now the what we have is the following. So I have a density, I have a quantum state. So I have a quantum state rho, some subatomic particle. Okay, think of it like that. Preparation of some subatomic particle. Now I have a qubit pipe. Okay, so this lives inside HA. Okay, I have a qubit pipe of it's in kind of the dimension tells you its ability to transmit, right? Higher dimension means it has more ability to transmit, because you can send, if you have 2 qubits, I need D H C2 tensor C2, right? This is the space of 2 qubits, right? If I have k qubits, it is D C2 tensor C2 all the way until CK. I should be writing the 2 at the top. And so this is of dimension 2 power k. Now, so higher dimensional, if I can input a higher dimension, let's also assume that the CPT map is perfect. So E is E of rho is rho. So you input rho here. Sorry, you input some density operator sigma here. You get sigma out here. Okay. The only thing is the dimension of this is more constrained. Okay. So rho is in D of HA. This CPTP map takes you from so let's say L of C2 to C2. Okay. The question is, how many times should I use the CPTP map to send this rho across the channel? That's the goal. So you have to send this quantum state perfectly across the channel. It's not, you have bits or anything. You have a quantum state, you have a CPTP map, can I send this across the CPTP map? So clearly, if dimension of HA is less than 2, there is no problem, right? But if dimension of HA is, because if dimension of HA is less than 2, you can always enlarge it with an isometry. So you pass it through isometry and then you do a reprojection, right? You can always do that. So you can take an isometry U, take rho, U dagger. So this takes you to a dimension 2 and you do a projection and you get back what you want. Is that clear?
So
But
the isometry we are using is to like to C2, changing it the
yeah, so
dimension.
the C2 is not a good example. So let me take, okay, let me do one simple thing. Instead of C2, okay, just 1 second. So I will take the CPTP map to be E goes from L of C 2 power L. Let's say 2 power L. Let's say D. Let's just say H of dimension D. Okay, and rho lives inside L of HA. HA has some dimension, say R. Dimension of HA is R. Okay, and dimension of HD is D. Yeah, now Srinidhi, go ahead and ask your question.
Yeah, now I understood. Like if R is less than D, like we do an isometry and then we send the new one through the channel and then do reprojection, right?
Yeah, because in that space it remains unaltered, right?
Yeah.
Exactly.
Yeah.
So you can do that. But if R is greater than D, what do you do? Suppose. So this naive scheme tells you that, so naive scheme.
Sorry, just one question.
Yeah.
So we are supposed to send rho across, right?
Yeah, whatever quantum state you want to send it across.
So if R is more than D, then we cannot possibly do it using this E because the output of E is in H of D.
Correct. But you can do something here, right? Can you squish it down? And you can maybe squish it back up here.
Okay.
It's possible. In theory, it is, I mean, there's no reason why it can't be. You can possibly squish it down and you can possibly squish it up. And still retain it as is. That's the whole thing. Right. So this is very similar to your compression problem. Remember your compression problem. You have data coming in some set X, and say it takes values in 0, 1, 2, 3. You have classical registers. So every time you get one bit X, you get X1, X2 to Xn. Every time you get a symbol, I'll call this a symbol. You have one register in which you can store it. One classical register. The question is, can you store it, right? Clearly, it appears, if you don't do anything.
So was the goal to come up with a way to like compress it and decompress it, or just like get it to a dimension D space?
Yeah, the
so that you
goal.
Separate states. What is the goal?
Yeah, the goal is the following, right? So I'll tell you the goal. So you have a state rho, right? It is part of a big purification phi rho. I want to apply some transformation on the system that I can access, E, on phi rho. So now if I look at the dimension of the trace R of this has to be less than or equal to D, and I should get a recompression, you can call it a decompression. I'll call it a delta for decoder and E for encoder. So when I do IR tensor delta on IR tensor E operated on phi rho, this has to be very close to phi rho itself. This is the goal.
That's it. Yeah.
Does it kind of make sense?
Yes.
So
And the
so the idea is
any state. Like they're not coming from any. The phi rows can be any state.
Zeros can be any state whose, if I
Like,
trace out the reference,
I
I
mean,
get row.
as in, are we? Okay, fine. Yeah. All right.
So yeah,
Sorry.
so a row is known to everybody.
Sorry, one question. This
Yeah.
dimension of trace of that means what? Like that is some state which will be living in the Hilbert space HA.
Yeah.
Trace R of IR
No.
tensor applied to that phi row.
No. So phi row. So if I look at phi row, right? If I do a trace over R and I look at the dimension of this, I'm going to get R.
Yeah, so like that's not that's some
But
like what do you mean
no,
dimension?
but I'm applying E on it. I'm applying E on it.
Okay. Oh, so it's a vector subspace which you're getting at the end of it. Okay. No.
So no. So this is a state, right?
Yeah, that's one state, correct.
If I apply E on the component I see, so if E of LA HA to say L of, let's say it is HD, dimension D, suppose, then if I do this E operated on this,
yeah,
I trace out R, where will I be?
You will be somewhere in L of HD.
L of HD. So if I look at the dimension of this, what will it be?
Yeah, that I'm not under. Like, what do you mean by dimension of a state? Like, you mean rank or something? Like
yeah,
that's,
I mean, so
I mean,
yeah,
that's some
exactly,
density
right?
matrix.
So yeah, I mean the space in which it lives. Yeah, you're right. I should look at.
Okay.
Let me look at the. I should not look at the trace because it's not a projector. But if I look at the dimension of that subspace, yeah, that's a good. I mean,
Yeah,
it's not
I think I get it.
technically
You're just
correct,
saying which space it belongs to. That's what you're saying. Okay.
yeah, I'm looking at the dimension of that subspace.
Okay, fine.
Is that okay?
Yeah. Now it's clear.
Yeah, so that's a good point. So I should be looking at the dimension of that subspace on which it lives. So what do I want? I can always squish somebody. Okay, I can always squish somebody. So you take, suppose, rho lives inside D of HA. Okay, and HA, an orthonormal basis for HA is, say, EX. Some orthonormal basis for HA. I can always take my EXs to be, say, some arbitrary 0. Let's just say 0 EX. Okay, I take this, and if I define my E to be EX rho EX dagger, then clearly what I'm getting is I'm just going to get a 0 state. You can show that, this is a CPTP map. So if you just do EX dagger, EX, you're going to get summation EX. Okay, so this is a CPTP map. So this is a CPTP map, X belonging to X. When I apply this map on rho, what am I doing? Everything is just getting squished to 0. So I'll end up getting this, which means my E has killed this quantum state. Clearly, the dimension of what comes out is definitely less than D. So if this was my E, this is definitely, less than D. Well, it's actually 1. But I can't get this. So I need some way to get back the original state after doing some post-processing at the receiver. So this is, so this is what I get. So what? So let me explain this. So you have this quantum state rho. You apply your encoder map E, and you're going to get something, right? So you have a reference. You have a reference with that. So essentially, this whole system is going through an IR tensor E. So you're going to get some other system. Right? You have access to only what is below this line. And then you pass this through your identity CPTP map. So it's an identity CPTP map. So I'll just call it I. And then out comes this particle, the same particle, right? Now you want to apply an F map on this, or let's say a delta map on this. So it's going to be IR on the reference, so that what you get is identical to what you started with. This is the goal. So this state and this state must be close. You're applying an E, you're applying a delta, and you should squish, but squish without losing information. Is that okay?
Yes, sir.
Okay. That is the question. And so what naive scheme, you do the isometry scheme, naive scheme. Naive scheme requires R to be less than or equal to D. Suppose R is greater than D, you can't do it. Not possible. Right? What is your guess? Is something possible when R is greater than D? And if so, what is your idea? You actually know the answer to this. So I will let you guys think. First of all, put a thumbs up if the question, setting, problem, everything is clear. Next. Okay, so I'll ask you one question. Maybe you would, I don't know why nobody asked me this. I myself didn't ask this in the beginning. I myself made a mistake when a long time ago. Is okay, so remember, rho is known to everybody. Rho is known to everybody. Okay. The question is, why not just, Bob, simply prepare another particle with density operator rho? Doesn't that solve the problem? Why do all this communication and all that? Rho is known to everybody. Why not just prepare the state rho at the decoder? At the decoder, and then I'm done. Why? What is wrong with that? Huh? I don't know if it's my problem or your problem. I'm not able to hear you. Niranjan, go ahead, speak. I'm interested to hear. Or chat, or put it in the chat if your network is bad. Can you hear me? I mean,
I can hear you.
Huh?
I can hear you. I can hear you.
Okay. Are you also hearing Niranjan broken?
Yeah, it's broken. I think there's some CMI issue today. There was some email about it.
Yeah, I saw that, but it was at 3 o'clock, right?
Oh, I know.
Hello.
Yeah, Niranjan, go ahead.
Sir, can you?
Why don't you put in the chat?
I just missed.
Huh? Oh, I should have actually. Okay, let me. No, I think Niranjan, I think the network here with you is bad because others are able to hear it. Srinidhi, what about you? Are you using the CMI or what?
Yeah, I'm using mobile data.
Okay.
Sir, can you hear me now?
He has to prepare a purification. Yeah, I'm able to hear you now.
Yeah, so like he has to prepare a purification of rho, not rho itself, right?
You're in the right direction, but that's not the right statement.
Oh, okay.
He can prepare. I mean, when you prepare row, there is some purification, right?
Yeah, but like there'll be many different purifications, so they could be like not very close to each other.
You don't even know what the purification this guy also has, right?
Yeah, so like Bob can't just always prepare the same, like just start off with row and then prepare the exact same purification. That's what I was saying.
Okay, I think you're thinking correctly. Maybe not able to. Maybe this is the right. Maybe this is one way I put it. Maybe you're each one puts it differently. See, a quantum state, right, is actually entangled to the reference. It's always entangled to the reference. If you see this, right, this is phi rho. This is and when I trace out the reference, I get the particle. I get rho. So it is always entangled to the a state is not by itself. A state is its complete reference also. So what you want to do is whatever Bob gets here has to have the same entanglement with that. It's not that he can just prepare another state. See, the point is, if I take 0, 0 plus 1, 1 divided by root 2, and if I take this state, if I trace out the B part of both these guys, the quantum state is the density operator is identical. But this state is different from this state. And so if Alice had this state, I mean, Alice had, she had, I mean, essentially the reference plus Alice's state was this. Bob has to get exactly the same thing with his reference. I mean, not with his reference, but with the same reference. So in other words, this component, I mean, it's not the right way to say it, but the second component must be transferred out to Bob. You see that?
Yes, sir.
That is the key. So a state, so I mean, yes, this purification is also rho, this purification is also rho, but when Bob prepares this purification, I mean, prepares the state, it could be, that the state is actually, the full state is actually this. And it is completely unrelated to this. I mean, these two are completely orthogonal. This state is orthogonal to this state. Though your...
So, this is what I was saying. Like the row can have like two different purifications, which may not be very close to each other. So just with row, I can't prepare the same purification.
Okay. But I think more important is, yeah, I mean, but see, yeah, you can put it that way. It has to.
Yeah, I mean, like what you said makes a lot more sense. Like that, like what I said, just like intuitively thinking. Sorry.
Yeah. I mean, I don't know. Yeah, I agree. I will think about it. It's a good point. The way I thought of it is that, yeah, so when you pass it through this E map, right, the entanglement has to be preserved. So this entire system has to be preserved. It's not only this component has to be preserved. Yeah, but it's a good point. I'll think of what you said, because see, Niranjan, what is happening is you are passing the entire system through SCP-TP map. So you're passing it through the I tensor delta preceding I tensor E. So this has to be like the identity map. So in other words, the reference of this guy is also the same thing. I mean, well, again, the notion of reference is kind of weird, right? But it's the same thing. So, and so this has to be kind of close to I. Maybe that's the way we should put it. IR tensor A. Maybe that's the way we should put it.
Yeah, that makes sense.
Yeah. Okay, great. So we, okay, now the question is clear. Why we are taking the reference, I kind of argued to you. So it's not that simply this guy goes create a row. Doesn't help, because it could be, as I said, it could be like this. Okay, what is your guess? You know all the tools. You actually know the answer to this question. You know the complete answer to this question. You actually know what you will do also. You know everything.
So are you allowed some error?
No, I mean epsilon error. Epsilon, I mean, it should go down to exp minus n times. I mean, you can take multiple copies, okay? So you can take phi rho tensor n. So you can take n preparations, and you can take the purification of that, and you have to preserve that. That should give you some idea. IR, so tensor n, everything tensor n, E, so the delta, big delta, big E, operated on phi rho tensor n. So I take, nature is, I wait nature to prepare n states. I'll wait for it, and then I want to ensure that Bob gets it. But the pipe that connects me to Bob is has lesser, in some sense, capacity, right, than the dimension.
So like if you do some gentle measurement on some and the state which you get has smaller size, like projection on a small, and then you send that, and so then the perturbation will not be very big because it is by the gentle measurement lemma basically.
Yeah, you're on the right direction.
But okay. So how to make this into a CPTP? So the first measurement is a CPTP, the gentle measurement. And then that is sent, right? Yeah, but then the post processing to get back, that is, I'm not understanding. Like how to do that is not clear. After you squish it, how to get back the bigger state? Yeah.
What is a gentle measurement?
Oh, you can do it on the typical subspace of this row.
What is the size of that subspace?
2 raised to n of S of rho.
So what can you do? So if I wait for n, states, right, I am going to get a particle whose dimension is n, d power n, whose dimension is d power n. If I wait, so now my channel also gives me so much space. Sorry, it's r power n, not d power n. Sorry. So r is your state. So my state is so rich that I need a space of dimension r power n to describe it. That's what my space has become. But also I'm permitted d power n. So I can write this as n log, I can write this as 2 power n log r. This is 2 power n log d. Unfortunately, it turns out log r is greater than log d. But you were talking about some other quantity. What is that quantity?
The entropy of rho.
That is the space of your typical subspace.
Yeah, size of typical subspace. Yeah.
So S of rho is in general between log r and 0, correct?
Yeah.
It could be less than log d. Yeah. It could be. Will that help?
Yeah. Then
what you will do?
Then we are done. Then when you squish it, you get 2 raised to n S of rho, which is less than 2 raised to n log d. No, you're saying S of rho is less than log d, right?
Yeah, sorry, you're right. Yeah, correct. S of rho is less than log d. So then are you done?
Yeah, then when you do the gentle measurement, what you get will lie completely in the typical subspace. So yeah, so that rank can be at most like
2 power n log d.
Yeah,
That rank is going to be at most this, or at most close to this, which is less than this. Then you can do an isometry and push it here. Right.
Okay. Okay.
And then you come out, and then what do? You leave it like that, or what?
No, that is the point I'm not understanding. Like, I don't know how to do, because you want to come out to a 2 raised to n log r space.
I mean, the others are getting any ideas? Did you follow? I mean, did you follow what he's trying to say? I mean, Niranjan and Shridi, are you thinking that it's not clear how you will make it a CPTP map, and then how you will ensure that the reference is
You can just append some common string.
Huh?
If you just append some common string like zeros to all of them, that will not change the distance.
Okay. For some reason, the others are not.
I followed up to now. I was thinking on that, how he enlarges it.
Okay.
Appending zeros to the.
Okay. So Srinidhi, is the idea
like what he told is still not clear to me.
See, what he's saying is, I mean, he's not telling everything. I mean, he's not nailed it clear perfectly, but what he's telling is this. He's saying, okay, suppose I do a CPT, suppose I do a gentle measurement. Then he started with the gentle measurement. Gentle measurement doesn't preserves the state, with high probability. I mean, not with high probability, but you do a gentle measurement. If you get the outcome corresponding to the highly likelihood guy, then your post measurement state is close to the original state. So he's saying, let's somehow come up with a gentle measurement. So then I asked him, what is a gentle measurement? And he said, let's do projection on the typical subspace. And then he knows that the outcome of the so if you take the typical subspace pi, and if you take I tensor n minus pi, then this has very high chance, first thing. Second, when you are squished into this, you're lying inside completely this, which means the dimension is less. So he's got to a point where he somehow post measurement is close to the original state. That's what he's saying. Now I don't know how to tie up. Is that clear so far?
Yeah. Yes.
That's his idea.
But why can't we just include the lower dimensional space into the larger one? It should. The gentle measurement will assure us the distance is still low, right?
Yeah. So now you're kind of giving a proof, actually. In some sense, you are including this, right? And you're trying you're trying to show that's exactly kind of the way we'll go. That's exactly what we'll do. So we have to find a way of kind of inflating it back. You kind of deflating it, and then you're kind of inflating it back. This is indeed going to be the solution. That's really all there is Schumacher compression, but I'll do it formally. And so the statement is that you can communicate as long as D is less than equal to S of rho. Log D. And if log D is greater than S of rho, you cannot do anything. Not possible. And this result is tight. So you are giving some kind of a characterization on the information content of this quantum state, because your pipe, your dimension log t is the size of, the how rich a quantum state can go on this CPTP map. And though your R, log R is greater than S of rho, really in some sense, the richness in the quantum state is only S of rho. And that's all you need. So that's really, the theorem, the Schumacher theorem, and I will do this. So the next class will be on Wednesday. I will hold the next class on Wednesday. I'll send out an email right now. So possible. Is the statement of the result clear? Problem is clear to all of you. The statement of the result is clear.
Yes.
And we will do, and the technique is also kind of evident to all of you, in the sense, I mean, it's not going to be a measurement, but it's going to be a CPTP map. But the CPTP map will mimic that measurement in some sense. One of its operators will project on the typical subspace, and the other one will not. So, I mean, you will design an ET, a collection of ETs, and then there will be an DT at the decoder that will kind of inflate back, because what you have done is you have essentially in the typical subspace, you have just done it inside the typical subspace. You are just doing a kind of a unitary map. Outside the typical subspace, you're killing it. And then what you do at the decoder is you rotate it back inside the typical subspace and don't worry about what is there outside. That's essentially what will happen. So, though you are, so it's kind of like this, right? I mean, though your density operator lives in 3 dimensions, it really is almost along kind of a plane. So it's kind of it's not good. I'm not a good person to write this. It's almost along a plane. And what you do is you keep everything in this plane intact. You squish everything back to somewhere, 1 dimension, and you keep this plane intact, and pretty much the whole density operator is preserved, or rather the state is preserved. So you kind of figuring out where is the non-triviality of this of this quantum state, or where are its details in some sense. The other places there are no details. It's in some sense like that. Is this okay? I will do the Schumacher compression I'll do the proof of the Schumacher compression in the next class. Essentially prove this theorem, and then we will go into something slightly more, slightly different. Okay, I will stop the recording.